In the video for step number 3, we saw the steps for testing the initial feasible solution for acceptability. That is, whether the initial feasible solution is acceptable to proceed with optimality test or not. Since the case that we have on hand proved to be acceptable for an optimality test, we then move to step number 4a, which is testing an initial feasible solution for optimality. In that step, we saw that there are two methods for testing for optimality. The first one is the stepping stone method and the second one is the modified distribution method. And in step 4a, we saw the stepping stone method in detail. Now in step 4b, we'll see the modified distribution method for testing an initial feasible solution for optimality. Now the table here is the initial feasible solution which has been tested for acceptability as per step number 3 and was found to be acceptable to proceed for an optimality test. Now in this stepping stone method, we first created a closed loop path for each unoccupied cell. Then we evaluated each unoccupied cell to find out the net costs change, and then chose the cell with the most negative evaluation. So since we have to formulate a closed path for each unoccupied cell, the stepping stone method is very time consuming. In the modified distribution method, we first evaluate all the unoccupied cells simultaneously and then formulate the closed path for the cell with the most negative evaluation. So this method turns out to be much quicker than the stepping stone method. So let's look at the detailed steps involved in the modified distribution method, which is also known as the MODI method or the UV method. So step number 1, set up a cost matrix containing the unit costs associated with the cells for which allocations have been made. Set up a cost matrix containing the unit cost associated with the cells for which allocations have been made. So this is how the matrix will look like. So I have only brought the unit cost of the cells which are already allocated in the initial feasible solution. So like AP has an allocation, so I have brought down the cost of 2. AQ has an allocation, so I have brought down the cost 3. BS is allocated, so I have brought down the cost 1. Similarly CP, CR and CS. Now let's move to step number 2. So step number 2 says assign the variable UI, where I is 1, 2, 3 and so on, to each of the rows, and VJ, where J is equal to 1, 2, 3 and so on, to each of the columns. So assign the variable UI, where I is equal to 1, 2, 3 and so on, to each of the rows and Vj, where j is equal to 1, 2, 3 and so on, to each of the columns. So let's say this is u1, u2 and u3, and this is v1, v2, v3 and v4. Now let's move to step number 3. So step number 3 says compute the value of u and v for the stone squares such that ui plus vj is equal to cij. So compute the values of u and v for the stone squares. Now stone squares are the ones which have an allocation such that ui plus vj is equal to cij. So u is this variable, v is this variable, and cij is the cost associated with the cell at the intersection of ith row and jth column. Now, if we look at the number of variables we have taken, we have, let's say the number of rows is m. So m is equal to 1, 2, 3, and number of columns is 4. So n is equal to 4. Now we know from previous videos that the number of allocations is m plus n minus 1, which is equal to 4 plus 3, 7 minus 1, which is 6. Now since we have taken 7 variables, we have the flexibility to assume one of the variable arbitrarily. So here we can choose the value of v1 as 0 so that we can find out the value of other variables here. So based on this formula, ui plus vj is equal to cij. Let's take the first row and first column. So u1 plus v1 is equal to 2. So u1 plus v1 equals to 2. u1 plus v2 equals to 3. u2 plus v4 equals to 1. u3 plus v1 equal to 5. u3 plus v3 equals to 15. And u3 plus v4 equals to 9. Now we have assumed that v1 is equal to 0, so let's find out the values of ui and vj's. So in the first formula, v1 is equal to 0, so that means u1 is equal to 2 and v1 equals to 0. Now u1 is known, u1 is 2. So v2 is equal to 3, and we can bring this 2 on the other side. So 3 minus 2. So v2 is equal to 1. So u1 is equal to 2 and v2 is equal to 1. Now for the equation u2 plus v4 equals to 1, we don't know the value of either of these two variables. So we'll skip this for now. The next equation is u3 plus v1 equals to 5. v1 is already 0, so u3 equals to 5. and V1 equals to 0. For the next equation, U3 plus V3 is equal to 15, U3 is equal to 5. So V3 is equal to 15 minus 5, which is 10. For the next one, U3 plus V4 equals to 9. U3 is 5. So V4 is 9 minus 5, which is 4. Now let's come back to this equation. So U2 plus V4 equals to 1 and V4 is 4. So U2 is equal to 1 minus 4, which is minus 3. And V4 is 4. So this is the matrix that we obtain in step number 3. I've placed the values of U1, U2, U3 and V1, V2, V3, V4 in the matrix itself. So V1 was 0, V2 was 1, V3 was 10 and V4 was 4. And similarly U1 was 2, U2 was minus 3 and U3 was 5. Now once we have obtained the values of U1, U2, U3, V1, V2, V3, V4, we then move to step number 4. So step number 4 is calculate the net cost change for each water square. So calculate the net cost change for each water square. Now what we did in the previous step was finding the values of Ui and Vj using the cost of the stone squares, which is the squares which have an allocation. Now in step number 4, what we are going to do is we'll take these values that we have found for Ui and Vj and compare them with the cost of the unallocated squares. So for the water squares, Ui plus Vj is considered as the implicit cost, while Cij is considered the actual cost. And the net cost change is equal to Cij, so the actual cost of the unallocated squares, minus the sum of the variables Ui and Vj. So Ui plus Vj. So let me note down the cost of the unallocated squares here so that we can easily calculate. So let me prepare a table. So the water squares are AR, AS, BP, BQ, BR and CQ. So AR, AS, BP, BQ, BR and CQ. Let's find out the values for Cij minus Ui plus Vj. So for AR, Cij is 11 minus Ui is 2 and Vj is 10. So 2 plus 10. For AS, Cij is 7. So 7 minus, again the same, Ui is 2 and V4 is 4. So 2 plus 4. For BP, the value of Cij is 1. So 1 minus, Ui is minus 3 and Vj is 0. So minus 3 plus 0. For BQ, Cij is 0 minus U2 is minus 3 and V2 is 1. For BR, Cij is 6 minus U2 is minus 3 and V3 is 10. For CQ, Cij is 8, so 8 minus U3 is 5 and V2 is 1. So let's calculate these values. So 2 plus 10 is 12, 11 minus 12 is minus 1, 2 plus 4 is 6, 7 minus 6 is 1, minus 3 plus 0 minus 3, so 1 minus minus 3 becomes 1 plus 3, so this is 4, 0 minus minus 3 plus 1, so minus 3 plus 1 is minus 2, and minus 2 multiplied by minus 1 is 2, minus 3 plus 10 is 7, 6 minus 7 is minus 1, 5 plus 1 is 6, 8 minus 6 is 2. So let's now move to step number 5. Step number 5 says evaluate the solution for optimality by reviewing the sign of the net cost change value. So evaluate the solution for optimality by reviewing the sign of the net cost change values. So now there could be multiple cases. The first case is if all the values are positive, then the optimal solution has been reached. So if all the values are positive, then the optimal solution has been reached. The second case is the negative value indicates that a better solution can be obtained by moving units into that square. So that means that if there is any negative value, of course, the solution is not yet optimal and we need to iterate towards optimality. So the negative sign indicates that a better solution can be obtained by moving units to that square. And the third case is that if the net cost change of more than one unoccupied square is negative, then for quicker solution, choose the cell with the largest negative value. So if the net cost change of more than one unoccupied square is negative, then for quicker solution choose the cell with the largest negative value. So in our case, we have two cells which have the same net cost change value of -1. The first one is AR and the second one is BR. Now if you compare the net cost change values obtained in this modified distribution method with that obtained in the stepping stone method, you will note that these values are the same in both these methods. So definitely, since we have negative values for net cost change, we have not yet reached the optimal solution. Now we'll have to iterate towards optimality in the next step, and we'll find out how to choose one of the squares between these two.